So in this lesson, if you have Ka, you will be able to find the Kb of its conjugate. So we're trying to figure out how are Ka and Kb related. Okay, so you have HF here. The conjugate base of HF is F minus. Conjugates, remember, are different by 1H. Okay, this is the acid conjugate and this is the base. So the acid and this is the base. They're conjugate pairs. These two react differently when added to water. When you add water, you put the H plus onto water and you get H3O plus the F minus, which is the conjugate base. When you take the conjugate base and you add that to water, the H will go to the base and you'll get HF plus OH minus. Okay, so these two are conjugates. The conjugate, oh, by the way, this equation can be also written as HF. If you don't write the water in, becomes another way of writing H3O plus is H plus this is F minus. So these two are the same thing. So HF is here. The conjugate, the Ka for HF is 6.8 E negative 4. This is its conjugate base, F minus. The Kb is 1.5 E negative 11. As you can see, since they're conjugates, these two numbers relate to each other in this way. Ka times Kb is equal to Kw. Okay, and what I will do next, I will prove that to you in the next slide. Remember, this relationship is only if they are conjugates. So since HF and F minus are conjugates, if you multiply these two numbers, go ahead and do that. 6.8 E negative 4 times 1.5 E negative 11. Go ahead and tell me what you get. So I wrote here 6.8 E negative 4, 1.5 E negative 11 equals 1.0 E negative 14, and that is Kw. If you do the same thing with acetic acid here, multiply this and this, you should get 1.0 E negative 14, the same with this, all of them, okay, because they're conjugate pairs. Now, the strong acid though, your Ka is strong, they just say strong, there's no Ka value, you can't find it, it's too big, okay, so which means if this is a strong acid, this is not even a base because strong acids give up all the H pluses, which means the conjugate base does not want it at all. So this base, this NO3 minus is not a base. Okay? So I'm going to prove it to you using this equation. So ammonium, when it dissociates, you're going to get H plus and NH3. And that is Ka. So Ka would be H plus times NH3 divided by NH4 plus. Okay, and this is the acid, it's a conjugate acid. Oops, the plus included, and this is the base. Remember, they're conjugate pairs. When you add the base with the water, the H goes this way, so you're going to get NH4 plus you're going to be left with OH minus. So that NH3 right now is acting as a base. This should be B. So Kb is equal to NH4 plus times OH minus over NH3. Okay, so what I'm going to do is I'm going to multiply this times this to prove that Ka times Kb equals K. So I'm going to take that and write it here. So that's the Ka expression. Here's the Kb expression. I'm writing this here. Okay, so as you notice, NH4 plus cancels with NH4 plus, NH3 cancels with NH3, so you're left with H plus right here, OH minus, and you know that that's equal to Kw, which proves that Ka times Kb equals Kw, and Kw is 1e negative 14. Okay, quantitatively, if 1 goes up, the Ka goes up, then the Kb has to go down to make it equal to 1e negative 14. Okay? Okay, let's go ahead and find Ka for NH4 plus, which is up here. It's 5.6, 5.6 e negative 10. So I'm going to write that here. 5.6 e negative 10, that's Ka. Kb is 1.8 e negative 5. You multiply that, you're going to get 1.0 e negative 14. Okay? If you take the log of this number, if you log 5.6 e negative 10, you're going to get 9.25. This is called pKa. Kind of like pH. When you log the H plus, when you log the Ka, it's now called pKa. Okay? Now, if you log this number, 1.8 e negative 5, 1.8 e negative 5, you will get 4.74. This is called pKb. pKb, because you logged it. If you add those two numbers, you should get 14, and that is called pKw. So pKa times pKa equals 14 at all times. So here's an example problem. Calculate the base dissociation constant Kb for the fluoride ion. So let's go ahead and think about the fluoride ion. If you look for Kb in the chart, in the appendix, so remember, these are all the Kas up here, dissociation constants for acids, Kas, and these are the dissociation constants for bases. And if you try to find F minus, you won't find it. And the reason is you don't need it to find it, because all you have to do is look for its conjugate acid. The conjugate acid of F minus is HF. So all you really need is this number, which is Ka. Okay, 6.8 e negative 4. So HF is equal to 6.8 e negative 4. This is the Ka of HF. Okay, it's the HF. Which means because HF and F minus are conjugate pairs, because these are conjugate pairs and because they're only different by one H. If they're different by 2 H's, you cannot use this trick, okay? Then Ka is times Kb is going to be equal to 1e negative 14. Since Ka is 6.8 e negative 4, you can find Kb. Oh, it's always uppercase K, okay? 1e negative 14. So Kb is going to be equal to 1.5 e negative 11. That is Kb. If you had F minus in water, what you will do then is you will do F minus, you will add water to that, and you will get, remember bases take the H, you will get HF, plus, and the H will be gone, and the OH will be left, OH minus. So you would do, let's say they told you a molarity of 0.1 molar. Just for example, you're going to do 0, 0. You're going to do minus X plus X plus X. And then you're going to do X, X, 0.1 minus X, and you will use this as your KB for the F minus. Okay, so that's how you use that. So please pause the video and try letter B by yourself. Okay, so B. The acid dissociating constant for ammonium, NH4+, is equal to, oh, find it. Find Ka. Okay, so all you have to do is go to the chart and find Kb. And the Kb of NH3. Notice, these are conjugate pairs. This has 4 H's, 3 H's are different by 1 H. So you have to find Kb using this chart, the appendix D. And ammonia has a Kb of 1.8 E negative 5. So this is 1.8 E negative 5, and you're trying to find this. So Ka times Kb is equal to Kw. Ka is unknown. 1.8 E negative 5 is Kb. Equals Kw is 1 E negative 14. So Ka, which is X, is equal to 5.6 E negative 10.